So here's our next video for the Higgs Boson particle quantum integer radioactive decay numbers chromodynamics QCD weak interactions 5G WOW SETI. All the videos will be linked together on the iDiogo.Says YouTube channel, and the blog posts get blogged on the Victoria Stafford website. The links will be with the video. So what we're doing in this one is we're going to Google quantum numbers because I want to know what it says. So it's a quote from Wiki. Quantum numbers describe values of conserved quantities in the dynamics of the quantum system. Perhaps the most peculiar aspect of quantum mechanics is the quantization of observable quantities, since quantum numbers are discrete sets of integers, or half-integers. This is distinguished from classical mechanics, where the values can range continuously. Quantum numbers often describe specifically the energies of electrons and atoms, but other possibilities include angular momentum and spin. Any quantum system can have one or more quantum numbers. It is thus difficult to list all possible quantum numbers. So the keywords in the data are integers or half-integers, plus energies, plus electrons, plus atoms, plus angular momentum, plus spin, plus quantum numbers, plus other formula. Comes up in the new Higgs Boson data and WOW SETI data. So the word for radioactive decay, there's the link for it on Google. From formula, idea, Flavours, the standard model. So I'm going to Google chromodynamics. So quotes from Wiki is, in theoretical physics, quantum chromodynamics QCD is a theory of the strong interaction color force, a fundamental force describing the interactions between quarks and gluons, which make up hadrons, such as the proton, neutron, or pion. It is the study of the SU3 Yang-Mills theory of color charts, fermions, the quarks. QCD is a quantum field theory of a special kind called a non-Albion gauge theory, consisting of a color field mediated by a set of exchange particles, the gluons. The theory is an important part of the standard model of particle physics. A huge body of experimental evidence of QCD has been gathered over the years. QCD enjoys two peculiar properties: confinement, which means that the force between quarks does not diminish as they are separated. Because of this, it would take an infinite amount of energy to separate two quarks. They are forever bound into hadrons, such as the proton and the neutron. Although analytically unproven, confinement is widely believed to be true because it explains the consistent failure of free quark searches, and it is easy to demonstrate in lattice QCD. Asymptotic freedom, which means that in very high energy reactions, quarks and gluons interact very weakly. This prediction of QCD was first discovered in the early 1970s by David Pulitzer and by Frank Wilczek and David Gross. For this work, they were awarded the 2004 Nobel Prize in Physics. There is no known phase transition line separating these two properties. Confinement is dominant in low energy scales, but as energy increases, asymptotic freedom becomes dominant. All the data has been divided up into different videos, so I do a certain set of words in each video. So this will be continued in the next video, and then of course after I get through all the words, I come up with a formula idea for you, okay? So thank you for watching. We'll go on to the next video now.